Hello everyone, this is Professor Felipe Rodriguez again. Today we're going to be talking about discrete event simulation. So let me bring up my screen and let's start. There we go. Here's the PowerPoint slide. All right, so let's begin. So this is MOS 3330, Operations Management, and the unit we're working right now is called Process Improvement, and the lesson is Discrete Event Simulation. As usual, you can email me if you have any questions. So this course is from the School of Management, Economics, and Mathematics from King's University College here at Western University, Canada. So, oh, there we go. I have to change this thing. You know what? I'm going to increase the size of this screen a little bit more. There you go. So, discrete event simulation. Readings, chapter 16 from Cashon's textbook. Again, this chapter talks about queuing theory. You could also include chapter 17. Chapter 17 has what we call queues with impatient customers, or what we call loss systems. Loss systems, right? Then I would also recommend this particular text called A Note on Queuing Theories by Professor Rasha Kashev and Professor Felipe Rodriguez. Me, a little bit of self-promotion there. So click on that link. It's a really nice teaching note, and it will be very helpful for you. There is a lot of intuition-based text over there, so we're not focusing necessarily on the mathematical formulas, but much more on how you build intuition with respect to queuing models. Then Simul8, which is the company that produces one of the leading softwares in discrete event simulation called Simul8, has this material from Schaliker and Ricketts called The Introduction to Simulation in the Service. There's also one for manufacturing industry using Simul8 2019. This is the release 26. That's the one I have available. So you can log in with your student account that I provided earlier. If not, let me know. If you're my student within this course, we have a license that you can log in and access Simul8 online, as well as some of those resources. This particular text is a really good tutorial and introduction to building simulations using Simul8. So, learning objectives for today, we're going to review a basic process analysis. Then, we're going to build the flow map, talk about demand, tech time, capacity, cycle times, find bottlenecks, and we're going to try to resolve some of those issues. But I would focus on this part. We're going to build a discrete event simulation software using Simul8. And then we're going to compare those results. The ones that we can get from the traditional formulas where we don't have any variability in the process, or even if we do have variability in the process, we can use, for example, those TQ formulas that I showed before. We can use Little's law, inventory equals flow rate times flow time, right? And then we can compare the results with what we find from the simulation. So the idea here is the discrete event simulator provides a lot more intuition and a lot more insight into a process analysis improvement. And we're going to see when it's appropriate to use discrete event simulation models and when you may not need to use that as much. So a few things to remember. We're matching supply and demand, right? So with people, planet, and profit in our minds, there's always two broad strategies that we can look for, and differentiation and cost leadership, they require completely different operations, right? You cannot manage what you cannot measure. So the idea here is if you have key performance indicators, you can therefore make decisions. If X happens, then Y happens. So if you change X, what's going to happen to Y? And if you understand these relationships, then you can make decisions, right? The process triangle, inventory, capacity, and variability. This comes from Little's law, right? So the length of the system equals its flow rate times flow time. When we're talking about operations management, we say that the inventory equals the flow rate times the flow time, right? So it's the same thing. Inventory, capacity, and variability, they form, therefore, the process triangle, right? And when these things are unbalanced, you end up having wasted inventory, utilization goes all over the place, and you have excess variability. And queuing is particularly good in these cases because as you add variability to processes, things become less predictable, and therefore using discrete event simulations allow you to play a little bit more with that variability and see the impact of that variability in your process, right? And that's an excellent tool for continuous improvement. There's always a better way, PDCA. So all these cycles, DMake and whatnot, there's always a better way to manage a process. There's always value to be added. And last but not least, operations doesn't happen by itself. It has a direct link to finance, to marketing, to human resources, and particularly, let's think of operations as a way to improve your cost of goods sold and therefore improve your gross margin. We're adding value and therefore improving our margins. So we talked a little bit about queuing theory and how we can find the time that you spent in queue, and from Little's law, inventory equals flow rate times flow time. So if you know what the time in the queue is, you know what your inventory is. And a lot of times we call these guys work. Oh my God, I apologize. This is really, really bad. Let me erase this thing. So work in process inventory, right? So if I know the time a unit spends waiting for service, I can therefore, from Little's law, calculate what the inventory will be at that step of the process. Few important things. M, number of servers. So if M goes up, this is the denominator. Time in queue goes down, so bigger systems work better. The utilization rate, bigger systems showing up over here as M increases, the utilization rate becomes less, the time in queue becomes less sensitive, right? So bigger systems improve. There is diminishing returns to scale because of this square root that we see over here. And the big deal comes from this guy. The coefficient of variation or variance is squared. So any changes, if you add variability in the process, your time in queue will increase, and therefore your inventory. So variability, as we know from the process triangle, as you increase this, you increase this guy. So variability is your number one enemy for your COGS. Never forget about this. Okay, so as I was saying about Little's law before, we can therefore calculate the inventory in queue, inventory in process, and total inventory. So why don't we do a little bit of a process analysis right here, okay? So this is a simple example. I have 3 workstations here, work center 1, 2, and 3, right? And I have a demand of 36 units per hour. So 36 units per hour, this could be my flow rate, right? And if I want to think in terms of takt time, this would represent a takt time of roughly, what is it that I have again? 100 seconds, 100 seconds per unit, right? That's my takt time right there. So I want to observe by the end of this process, every 100 seconds, 1 unit should be leaving my process. If it's a product, I'm shipping 1 unit to my client. If it's an order, it's going through. If it's a service, it's the end of the service, right? So here are the processing times. I have 90 seconds for work center number 1, 96 seconds for work center number 2, 93 seconds for work center number 3. So by looking at the process times by themselves, I can't really say anything because it seems that the work center number 3 has the highest processing time, the slowest process, so that could be our bottleneck. However, for each workstation, I have a certain number of employees. I have 1 employee over here, 1 employee at work center number 2, and 2 employees on work center number 3. So if I think in terms of capacity, so what is capacity? Capacity is P divided by A times M. I'm increasing the size of M, therefore I should be increasing my capacity, right? So the capacity in units per hour, 90 seconds per unit is 40 units per hour. 96 seconds per unit is 37.5 units per hour. And now I have 2 servers over here. So 150 seconds per unit with 2 servers becomes 48 units per hour. So let's think about this for a moment. My demand is 36 units per hour. So can I start thinking in terms of what my flow rate will be? So my flow rate is the minimum between my demand and my capacity, right? So the capacity of this this process, I gotta find what the bottleneck is. So the smallest capacity should be the bottleneck. 40, 37.5, and 48. So this is the bottleneck right here, 37.5, sorry. So my flow rate should be either 36 units per hour or 37.5 units per hour. So therefore, we know our flow rate is 36 units per hour. We are demand constrained, right? We have a little bit extra capacity. So we can calculate now our utilization rates. So 40 divided by 36. So this is roughly 90%, right? So in fact, exactly 9. Sorry, wrong place. Just a second. Here, I apologize. There you go. Okay, so utilization rate, 36 divided by 40. This is 0.9. This guy is 36 divided by 37.5. This is 96% or 0.96. Let me move my little guy over here. Okay. And third guy, third work center over here, 36 divided by 48. And this is equals to 75%. Right? So the bottleneck is always the one with the highest utilization rate. So as we were saying before, work center number 2 is our bottleneck, right? So our cycle time, therefore, is 1, let's see, 1 unit every 100 seconds, right? So that's our cycle time, right? And that's how we go about it. Okay, so can we improve this process a little bit? What is it that we can do? Okay, first and foremost, we have not considered any variability just yet. So what happens if we add variability to this process, right? So far, we seem to be saying this is exactly 100 seconds per unit. This is exactly 90 seconds per unit, exactly 96 seconds per unit, exactly 150 seconds per unit. But what if it isn't exactly? What if these are average times? And what if these average times are constant? So we can add a little bit more variability to the process and see if we can get more insight from this process, right? So same process that I had before, okay? 3 work centers right there. I'm gonna put this down here for a moment. 3 work centers right there. Same demand, but now I'm adding a coefficient of variance of 1 for the arrivals and a coefficient of variance of 1 for the processes, right? So same units, same time, same everything. So I'm not going to worry too much about the utilization. I already know that. I already know what the bottleneck is. I know what the cycle time is. But I want to know if it can calculate how long each unit that goes through my process will be awaiting to be serviced, right? To be processed. So can I do this? I believe I can. So we can use a TQ formula that we know from before. So should I go back to the TQ formula? Let me go back to the TQ formula, and I will erase all these things so we remember what this formula is all about. Okay, so here's the TQ formula right there, Hoppe-Spearman formula. So we know there's 3 factors. This guy, this is capacity factor. This guy is the utilization factor. This guy is the variability factor. If I know the CVs are all 1, so 1 squared is 1, 1 squared is 1 divided by 2. So this becomes 1. So I don't have to worry about this part of the formula. I have to worry about this part of the formula only for the processes that have m equals 1. 1 plus 1 is 2, 2 times 2 is 4, square root of 4 is 2, minus 1 is 1, so this thing cancels out, becomes 1. For those that have more servers, then this becomes an exponent. So I can calculate the time in Q, and I have already calculated that for you before in advance. So I do know that my cycle time over here is 100 seconds per unit. I just want to have this as a base, right? And the timing queue for the first unit, considering this processing time and the inter-arrival time A equals 100 seconds per unit, right? So the timing queue for this guy, incredibly, is 110 seconds. For the next one, which has a really, really high utilization, if it's a 96% utilization rate, so this guy is 90%, this guy is 75% utilization rate. So let's see what happens to the timing queue. The busier you are, the more likely you are to have inventory waiting. So this guy becomes, work center number 2 becomes 2,304 seconds. So this is roughly about 1 hour. So in a process that takes 96 seconds, those flow units are waiting 2,300 seconds on average, right? So these are average results in a steady state, right? You see that things can fluctuate a little bit. Work center number 3 has the lowest utilization rate, so only 197.7 seconds, which is not that bad, right? So flow time, if you sum up this guy with this guy, you get the flow time for each unit, right? So 3,000, sorry. No, I'm gonna have all them summed up already. I apologize. I'm gonna skip that step. So I'm gonna sum these 3, right? Plus these 3. So I can calculate my flow time. The overall, this is not almost 1 hour. What we have is almost 1 hour is the total flow time, which is 3,648 seconds. This is how long this process takes. And we were thinking that this process would take this long, right? Isn't it weird? So that's all due to variability. That's the impact of variability right there. As we add variability, we make people and units and flow units wait a lot. So does the cycle time change? No, not at all. You will still see 100 units leaving that system 100 seconds per unit. You will still see that, right? That cycle time will remain. The flow time is longer, right? But the flow rate is always the same. You will see 36 units per hour. It will take on average 100 seconds per unit, okay? It's just that there will be lots and lots of units in inventory. That's what's gonna happen. And I can use Little's law to calculate the inventory in queue. So let's see, this one, 8.1 seconds. I can do this by hand because if I know it's 110 seconds, the time in queue, and inventory is flow rate times flow time, right? So I can calculate these two, and I know it's 8.1 units of inventory. This guy has 23 units of inventory, and this guy has 1.97. So remember, inventory is COGS, right? So that's your COGS right there. So that's cash flow. That is accounts payable, right? You had to purchase raw materials maybe. This becomes accounts payable. This is reducing your cash flow. Now you have to hold inventory. Inventory have holding costs and so forth. Okay, so now I added this extra layer. I know what my inventory is. You know, it doesn't make any sense that a process should take roughly about 1 hour to complete if there is only 90 seconds, 96, and 120, 150 seconds, right? It doesn't make any sense. This should be about 6 minutes, right? So how can we improve this? Well, let's attack the bottleneck. Let's attack this guy over here. This is my bottleneck. So here's my recommendation. What if I add one more employee to work center number 2, right? So that was the bottleneck. I'm increasing the capacity of work center number 2. When I do this, now with 2 employees, I have 75 units per hour in capacity. So what happens over here? Utilization rate, nothing changed, 90%. This guy just doubled my capacity over here. So my utilization rate drops from 96% to 48. Is it 48%? I believe it is, yeah. And the work center number 3 doesn't change anything, 75%. Okay, so now this is no longer the bottleneck. The bottleneck becomes this guy, right? Because that's the highest utilization rate. The cycle time is still 100 seconds per unit because this process remains demand constraint. Let's look at what happens to the time in queue. So nothing changes with this guy. We didn't add any extra capacity, so the time in queue is 110 seconds. Now work center number 2 drops from the original, I believe it was 2,300 and something, 2,304 maybe. And now this drops using the same formula. This drops to, what is that again? 31.9. So that's a huge decrease in the time in queue. And over here, nothing really happens, 197 seconds, 0.7. So your total flow time, if you sum up the P's and the time in queues, you end up now with a process that lasts 1,376 seconds. So now this is just 0.38 hours, much better than the 1 hour that I had before. What happens to the inventory in queue? Same calculation using Little's law, inventory equals flow rate times flow time. So the inventory in Q is the flow rate times the time in Q. So now same 8.1 units. The work center number 2 now has a significant change. So now I have 0.319 units and nothing changes over here, right? 7 units. So my inventory decreased a great deal. So what this means is I'm reducing COGS right there, right? So I added one more employee. So things became more expensive from a service perspective, right? But my inventory decreased. So if I look, I have a chart like this. This is number of servers. This is cost, right? So here's the cost of service. Here is the cost of weight, or cost of weight, which is inventory in the end. And now I'm looking at my total cost right there. So hopefully I achieved that minimum point, right? Now, here's another example. Can I do something else? Because this is still a very, very busy process. What if my demand increases? What am I going to do, right? I'm going to be busy very, very fast. So here's the idea. What if that one employee that I added before was shared between work center number 1 and work center number 2? So now I have 3 guys. I'm going to draw these 3 guys over here, 3 girls, doesn't really matter. 3 people, and they can either work here or work there, depending on how it works. So the number of employees now changes to 1.5 and 1.5. The capacity is increased. Again, capacity is increased. So what happens to the utilization rate? Well, there you go. So utilization rate for this guy over here now is 60%. Using the same calculation, so I'm going to speed it up a little bit more. The for this guy at 50, so 40 divided by 56.25. So this should be around 64%, give or take, and nothing changes over here, 75%. Excellent. Now, where is the bottleneck? Now, the bottleneck becomes this dude over here. Let's see if it makes any, if it's relevant for us to keep improving this process, right? Cycle time is still the same, 100 seconds per unit, right? Now let's look at the timing queue. Using the same TQ formula that I had before, now I have 79.8 seconds. This guy has 102.4 seconds. And this guy is still the same, 197.7 seconds, right? So the total flow time in this situation now has decreased. Flow time, when I sum all these 3 plus all these 3 over here, I end up with a flow time of 716 seconds, which is 0.2 hours, a much better performance than what I had before. Remember, the cycle time was still the same, okay? The difference is what happens to your inventory, what happens to your COGS, okay? That's the key. So the inventory in Q, this is 1.798 units. This guy is 1.024 units, and this guy the same 1.977. So my inventory overall now is roughly 2, 3, 4 units, as opposed to what we had before, something like like 32 units, give or take, in the initial of the process. So this is a much better configuration now that I'm sharing those 3 workers with these 2 work centers, right? So that's an example of how I can see things from an analytical perspective. Now, let's see if I can do the same stuff with Simul8. All right, so I'm gonna, how do I exit this? Let's see, how do I? Do I keep annotated? Yes, I want to keep things annotated. Okay, so now I'm going to go to Simul8. And I'm going to perform the same kind of analysis that I did there, but now I'm going to be using Simul8 instead. Okay, so let me make my mouse work over here. Just a moment. Okay, so here's Simul8. Let me hide this guy over here. Excellent. So I have a little bit of a, gotta put my notes in here. First thing that we gotta do with Simul8 is we go to data in rules, and then we go to clock properties. Everything that we were talking before for that process was measured in seconds. So let's measure everything in seconds and keep that one single measurement of time, the time unit, for all throughout the process. Now, sure, time format doesn't really matter. Can be time of the day, can be time only, percentage. I'm going to keep percentage just so we understand how far along we are in the simulation over there. You know what? No, I do not. I'm going to use time of the day. I'm going to make a digital clock. Oh, what am I doing? This guy, sorry. Digital clock. I'm going to have 7 days every week. And I'm going to start at 0 hours. And a day lasts 24 hours. So I'm assuming I have 3 shifts of 8 hours, give or take. That's the way to go. The warm-up period, I'm going to make this warm-up period really, really long. So if I'm measuring seconds, let's see, maybe 100,000 seconds should be enough. There are formulas in which we can calculate the warm-up period. I'm just going to use a really large number for now and hope that that is enough. Okay, so 100,000 units, and I'm going to collect results, always keeping the same simulation time, okay? Let me show you what I mean. The results collection period, we want that to be in the simulation time. So I'm going to collect results for another 100,000 seconds, and that should be okay. Now, the other thing that you must always do when you're working with Simul8, and if you're not worried about geography or the spatial aspect of your simulation, is you gotta unclick travel times. So the distance between the units that you're simulating doesn't impact your overall results. So, and then Simul8 asks, are you really sure you want to do that? I'm going to say, yes, I'm sure. This is not a blueprint. So we're going to keep it as is. So, all right, now I'm going to add a start point. So I just clicked over here on that start point arrow, added this over here. I'm going to double click, and a few properties are going to show. So we do know that our process starts someplace. So let's assume that my starting point is my demand. So I'm going to standardize the nomenclature over here. So this is a work entry point. Call it work entry point number 1. I always recommend you keep using these formatting and these standards. So when people see your simulation, they know exactly what that means. So when they see a WEP, they know it's a work entry point, okay? So work entry point number 1, the inter-arrival time, that's our A. So we know the rate is 36 units per hour. That represents 100 seconds in between units. That's our inter-arrival time. And because I know my coefficient of variation is 1, right? So this is equivalent to the exponential distribution. There you go. So my work entry point is over here. I'm just going to go to the graphics over here and say show. so it shows exactly what this means. Always a good measurement. When you open the simulation, you can see everything that is going on over there and their names. So I'm gonna add a queue, and then I'm gonna add, right-click here and create an activity. So this activity, I'm gonna double-click on this activity. This is a work center. So use the standard for work centers, work center. This is the very first one. We know the coefficient of variance is 1, so that's an exponential distribution. And for the first workstation, it's 90 seconds per unit, all right? So there's only one place in that workstation, so the effective number of activities is just 1. This is excellent so far, so I'm gonna click OK. And I'm gonna go back to the queue immediately before work center number 1. And I'm gonna go to results, because I do wanna know the minimum, the maximum. I'm right-clicking those, okay? And the average and the maximum number of units that have entered this queue, right? So the size of the queue, the TQ formula in Little's law only gives us the average. With the simulation, I can see exactly how the distribution of those are. And I also want the queuing time, the minimum, the average, and the maximum, and why not the standard deviation too. And you know what? Let's add a little graph over here. I'm gonna put this guy down here so we know what we're talking about. So, I added this graph. Okay. So there you go. All right. Why does this thing showed up? Hide minimum controls. Excellent. So from workstation number 1, there's another working process area, right? So I'm going to create a queue and another activity. So same thing that we had before. This is going to be called now work center number 2. And work center number 2 also has a coefficient of variance of 1. So we can call this an exponential distribution. And the processing time was 96 seconds, okay? Work center number 2 has only one spot for one employee, so that's all we care for this moment now. You know what I'm gonna do? I'm gonna show this queue. I'm gonna show these names. These are nice names to show. And here at queue number 2, I'm also gonna collect the same kinds of results. The minimum, the average, and the maximum number of units in queue. So that's my working process inventory. And I'm going to add the queuing time, minimum, average, maximum, and why not standard deviation. Since I have a graph for the first one, I'm going to add a graph for the second one too. There you go. Okay. Oh, I know why this is happening. Every time I press escape, the Zoom commands show up. So from workstation, work center number 2, I have another queue, I have another activity, and then the process ends. So let me go to work center number 3, work C number 3. Did we change the error? I think we did. So for this guy though, it's 150 seconds exponential distribution. And I do know we have 2 people. So I'm going to add 2 activities. The replication here is 2. So there's 2 activities, in fact, within the workstation, right? Excellent. Now I'm going to go to my queue. I'm going to go to results, minimum, average, and maximum number of units in inventory. And then also minimum, average, maximum, standard deviation for the time in queue, the queuing time, plus a nice little graph right there. I'm gonna add this dude over here. Yeah. Okay. Nice and pretty. Why not? We are here in the queue, so I'm going to show the queue name, and this is the exit point. So similar, we have a work entry point, WEP. We have a work exit point, WEX, and I'm going to collect results here too. The minimum time in the system, the average time in the system, the maximum, and the standard deviation. Okay, so I'm gonna hit OK. One thing that I haven't done yet is save this file, so I'm gonna save it right now before I lose anything. So let me call this example one. I'm gonna put that in my desktop. Excellent. All right, so let's see what's going to happen right now. I will go to home. I'm going to try to set up. So my trials are going to have, you know what, I'm going to start with just 50 runs. You can always calculate the number of runs in a trial. Use the trial calculator. Our main key performance indicator is the average time in the system, so that's going to be my KPI. And I'm going to ask Simul8 to figure out for me how many runs I should have for each simulation, so I have enough of a distribution that compensates for all the randomness, right? So hit OK. So let's see what's going on right there. So it's slowly converging, and hopefully it's going to show to me how many simulations I need. So we're around 300. This sounds like a lot. I would expect something like 100 runs should be all right. So it's converging towards the mean over here with the confidence intervals right there, right? So this process can take a little bit of time. Let's just keep this running for a little bit, see if it converges faster. I believe the moment we hit the gray area right there, we should be okay. So let's see what's going on. So while this is doing it right here, I'm gonna go back to my, write down some of these measurements are important. So the first example, let me write this down. First example, the original system, I have a flow time of 3.648 seconds and inventory of about, let's see, 23 plus 8, that's 31 plus 2, about roughly 33 units of inventory. Then we solve the bottleneck. For the first time, our flow time goes down to 1,376 seconds with the inventory of 8 plus 0.3 plus 0.7. So this is 8.5 plus 2, give or take approximately 10.5. And then when we share the employees from Work Center 1 and 2, we get to a flow time of 716 seconds. And the inventory is roughly 4 units. Okay, so let's see what Simul8 is all about. So average time in the system, so it's recommending 431 runs. So let's see what we get from here at the work, the entry point. Average time in the system. Average time in the system. So it's giving us a range between 3,232 seconds and 3,055. So it gives us the distribution of how this goes. Now, the interesting thing is, from the TQ formula, I had originally 3,648. So this is showing that it's a little bit lower. Maybe there's some kind of parameter that we haven't dealt with over here. So I'm going to double check. Work center number 1, 90 seconds exponential with 1 replication. That's okay. The inter-arrival time, 100 seconds exponential. That's also okay. Work center number 2, 96 seconds exponential with 1 replication. That's okay. Work center number 3, 120 seconds exponential with a replication of 2. All right, so this seems to be okay. Simulation seems to be running right. So our theoretical result was 3,600 seconds, give or take, but our results over here are showing an average time of 3,400, going to the upper bound that we had before, right? So this seems to be running relatively well. Now, we can also check in terms of number of units in Q. And I would like to show you that even though the average is 3,402 units, look how much it goes up. It can go up by, the minimum time in the system can be as low as 834 seconds and as high as 6,410 seconds. So it's almost twice as much, right? So why is that happening? That's all the variance that we added to the system. So the TQ formula and the flow times that we calculated analytically, they gives us a steady state average, while using Simul8 allows us to see how much this ranges, right? Now we can also look at in terms of the Q size. So for example, the first Q had an average size of 8. So we can also calculate that too. So Q for work center number 1. Compress this a little bit. Right, so check it out. The average Q size is 8.2 with a minimum of 0.04, so almost no Q whatsoever, but as high as 30 units, give or take 31 even. If we go to Q number 2, the average Q size of 20, our formulas gave us originally 23 units. So it's a little bit above what we calculated from before. And the Q for work center 3, the average Q size at 1.91, and we had calculated 1.97. So there you go, we have it right there. So the simulation seems to be running okay, a little bit on the faster side. So I'm gonna save this now. And now let's implement some changes, right? So the first change is we need to add 2 work center number 2 needs 2 employees. So I'm going to replicate this and say it's 2 and hit it OK. So just making sure our system is according to what we expect. 90 seconds for the first one, exponential with 1 replication. Work center number 2, 96 seconds, exponential with 2 units. And work center number 3, 150 seconds with 2 units, also exponential. Okay, so I'm gonna hit home, press reset. Gonna put this to the end of the warm-up period, and I want to observe what's gonna happen with our Qs right there. So we can see what's going on. This is relatively slow. I'm gonna speed it up a little bit more. So we see what's happening with the queuing time. Now that we have 2 resources on work center number 2, there's almost no queue forming over here, although there is still a queue forming on work center number 1, and we know what that queue would be like. Queuing time there is expected to still be at around 810 seconds, so it goes as high as 2400, right? So I just ran this simulation right here. Let's see what the results show us. average time in the system at 1036, we might need to run a trial. I don't want 400. I'm gonna make this 100 units for now, just so we can collect results a little bit faster. So I'm running 100 simulations right now with the same system. So we are changing seeds and incorporating all the variation in the system, right? Okay, excellent. So let's look at our key performance indicator. The average time in the system right now is 1213, but it goes as low as 67 seconds. How the hell did that happen? And as high as 3400 seconds going through. So this is incredibly long, right? But we know how this is ranging. And our initial calculations from our first, let's see, when we added 2 units over here, we were expecting to have 1,376, and the simulation is showing us 1,213. So it's a little bit faster than we expected. Right. But see, in the high range of 1,376, so we're getting close there, right? The simulation seems to be performing well, and we can look at the inventory also. So the inventory right here, average queue size is around 6 to 8 units. Our theoretical was 8.1, and then for Work center number 2, the average queuing size now drops dramatically. Our initial results was 0.31. So we're at the upper side of this over here. And for Q3, still the same average queue size of around 1.97. So we're still within the bounds that we expect. Excellent. Now, so the second, sorry, the first improvement we did in the process, which was adding 1 worker to work center number 2, seems to be behaving well. Now, the second option that we had was what if we could share resources from work center number 1 and work center number 2? So what if we had 3 employees, but they could both work at work center number 1 and work center number 2? So in order for us to do that, we have to create resources in Excel. Oh, sorry, in Simul8. So I'm going to do this right now. I'm going to use resources, and I'm going to say add a new resource. I'm going to call this resource number 1, and we're going to have 3 people on resource number 1. We have 3 resources number 1, okay? And these are going to be used for work center number 1 as well as work center number 2. Oh, they showed up here already, so I'm going to put them over here. Work center number 2, resources. I'm going to add resource number 1. There you go. So workers can go from work center number 1 and work center number 2 according to their need. So because I had 3 workers, I'm simulating that idea that I have 1.5 worker, 1.5 worker at each work center. That's what I'm trying to simulate right now as best as I can. So I'm gonna reset the simulation. Gonna go to, oh, you know what? Work center number 3 doesn't have any resources. So I'm gonna add a resource for workstation number 3. I'm gonna call this something else. I'm gonna call this resource number 3. And I know we have 2 employees there, so there's 2 resources there. Okay. There you go. You guys show up over here. And you know what else I'm gonna do? I'm gonna add a result I want a graph. I want the utilization of that resource. I also want a graph of the resource right there. Okay. And because I have the usage of resource number 1, I'm gonna want that too for utilization of resource number 2. I'm gonna add my graph over here. Okay, excellent. So I'm gonna save this guy for now, reset. Okay, go to the end of the warm-up period and run the simulation. Let's see what happens. So should probably hide this guy as I'm running my simulation. So almost, we don't see a lot of queues, a lot of inventory forming. It goes up and down a little bit or whatnot, but then you can see the utilization here. I'm using on average, give or take 1.8 of that resource out of 3. This guy on average 1.5. So 1.5 out of 2, that's the 75% utilization that we are expecting to have, right? And I just ran simulation. Now I'm going to run a new trial. Hopefully it's going to be fast. When you add resources, it kind of slows it down a little bit more. But the idea that having a resource is interesting because it allows you to look at the utilization of each one of those resources as an extra metric. Plus, it can give you the idea of sharing resources. So for example, if this were some sort of, say, a hospital, right? So it's a nurse. So a nurse can go to different beds. So it's the same resource going to different work centers. Each bed could be a work center, for example. Or this could be a call center where you have a customer representative and that guy can perform multiple roles. So it's interesting to add the resources because it gives you extra functionality as well as allows you, for example, to work with shifts. So the resources can have different shifts. We can also have not only shifts, but then there could be absenteeism with the resources. So they skip work, they become unavailable. These could be machines. This could be a whole bunch of things, right? So one of the things that I'm thinking right now is that maybe the simulation time is not long enough. So if I were to run a simulation longer, 100,000 seconds for warm up and 100,000 seconds for collection period may not be enough. So I'm gonna run this trial right now. If I still get results a little bit lower than I'm expecting, it means perhaps that I haven't reached entirely the steady state. So let's see what we get from these results, and see if we need indeed to test the hypothesis that it would take longer to reach a steady state. So what's going on with this trial right now? It's at 80%, but we're getting pretty consistent results, right? Utilization resource 1.86. 1.86 out of 3, so that's about 60%. Let's look at this guy. Let's see, 1.5. Yeah, 1.5 out of 2. That's about 75% utilization. There you go. Now we have results. So let's track some of these guys and see what happens. So I'm going to focus on the average time in the system. So average time in the system now. Let's see what happened. So the average time in the system now is 1,287, and I was expecting this to be 716, give or take. So this seems to be a little bit high. The utilization in terms of percentage points seems to be okay. So I think that maybe I should be running the simulation for a little bit longer. So I'm going to go to data and rules, and the warm-up period, I'm going to make this 1,000,000 seconds. And the results collection, I'll also make this 1,000,000 seconds, okay? And I'm going to run one simulation just to see how the behavior changes. Let's see. Okay. So I'm going to speed it up. Right. So you can see the queues forming over here, not necessarily over here, which is interesting. 1.79 utilization, 1.46. This seems to be okay. Yeah, so I think this is running all right. I'm gonna go all the way up to the end of the simulation and see how that result goes. Okay. Oh, please don't crash because I'm recording. I'm recording this video right now. I don't want this to crash. Oh, thank God. Sorry, I have a really old computer, so sometimes these things happen. Results manager. Let's see that one particular run. What is it that I get from this simulation? Okay. So average time in the system. Now it's showing, 1,500. I think utilization at 62% for resource number 1 and 79% for resource number 2. This is interesting. I'm finding this to be a little bit high. Let's see if I can spot what's going on right now. The average queue size for the first guy is, let's see, it's supposed to be, the average queue size is supposed to be 0.7, but it's still 0.9. So I think I just spotted my mistake. How many replications do I have for work center number 1? Oh, there's a mistake right there. Excellent. So I'm sharing resources, but I should be able to allow 2 people to be working at the same time at resource number 1. That's what it is. So now I have 2 spots at workstation number 1, and I can have 2 people working at the same time, but on average, they could be shared with work center number 2. So it's 3 resources to be shared with these 2 guys. I think now we're gonna be good. Let's see. I'm gonna go to the end of the warm-up period, and let's see how this goes. Pretty sure it's gonna be very consistent now. Okay, so 1.88 out of 3. This is roughly what we expect, around 60 to 64%. 1.49, this is also around what we expect. So let's look at the results manager. Let's see what it says. There you go. Average time in the system. All right. So this one particular run is 600 seconds, and I'm expecting 716 seconds, give or take. So what we know, the utilization seems to be okay. So it might be an issue with our trial, right? So we ran once. So maybe I want to run this trial again. So I'm gonna make it a little bit faster, just for the sake of time within this video. So let's see. Hopefully it won't take too long. Sorry. Okay, so we're almost done with this trial. Let's see what kind of results we get and compare that with the analytical results that we had from before. Okay, 92%. Excellent. Mhm. All right, there we go. So let's see what's going on right here. Okay, average time in the system now is running from 585 to 610. So this is more around the values that we were expecting before, around 700, 700 um, seconds, right? And utilization rate seems to be performing well. We were expecting between 60 and 65. So around 61, and for resource number 1, and for resource number 3, around 75%. So these results seem to be making sense. So let's see, average queue size of 0.47. Where do we get from? Let's see. So now I have a much lower queue. Queuing time. Let's see what the queuing time is. 46 seconds. That's one employee. All right. So queuing time around 79. So this is a little bit faster than I was expecting from before. And for the last one, average queuing time in the system 184. I'm expecting 147. So this system seems to be performing relatively well. Let's save this guy right now. And let's go back to the PowerPoint presentation. Oh, maybe I can reduce my, there you go. So let's look at what we had before. When there's no variance, we can't really calculate the time in queue, and we can't really calculate a lot of inventory, right? But as we add variance to the system, we can calculate time in queue and inventory, which allows us to understand in terms of what our flow time is. And if I know my flow time, I know exactly where I'm wasting time with queues, right? So all of this weight is non-value added weight. We shouldn't be doing this. Imagine if this is a hair salon, a dentist, or even a hospital. Imagine if this is a car wash, whatever, or a call center, or even a manufacturing process for that matter. All that time waiting adds absolutely no value whatsoever, right? So we're using the MMS system, which is memoryless in arrivals, memoryless in service, and with multiple servers. And as we add and we try to solve those bottlenecks, we can see what happens to our total inventory. This is COGS. Sorry. Oh my God, this doesn't look good. I apologize. Let me erase this guy. So what I mean to say is this is COGS going down, right? COGS going down, that is a key. So as I move, now I'm sharing the employee with 2 of these units. I have even less inventory. I have better cash flow, right? I have a lower accounts payable. I have a better COGS. Everything is improving from this system by understanding how those queues perform. So pros and cons of this discrete event simulation model. Oh, and by the way, I forgot to mention, when we solved this using Simul8, we found that these numbers were a little bit high. So we were a little bit below, around 3,500 in this case, a little bit below over here, 2700, and a little bit below over here, around 160 seconds, right? In terms of total time. Inventories were relatively the same, but also a little bit lower too. This was 35, this was 12, and this was 6, give or take. So the simulation results were on the lower side of what we were expecting from our analytical results. When do we use a discrete event simulation model? When is that good? Well, do you have to use a discrete event simulation model every time? No, you don't. So if all you need is a high-level calculation, if you're thinking in terms of balancing an assembly line, if you're thinking in terms of finding bottlenecks, sometimes, you know, good old process analysis and bottleneck analysis would suffice, right? This is going to give you big picture information, capacity and flow rate. This will tell you about takt versus cycle time. That's when you use a process analysis. When is it that you use a discrete event simulator model like Simul8, for example? When there's a lot of variability in the system, that's important. Another one is when you know the system is congested. So every time you have lots of inventory, discrete event simulation should be good for you. It will give you more insights about your inventory, right? It will give insights about people waiting in line. It's a toll booth, it's a call center, it's the emergency room, it's your restaurant and whatnot, right? More recent example, it's testing for COVID-19, which seems to be happening right now. Hopefully in the future, this won't be relevant anymore. But very importantly, when you are interested in terms of flow time and lead times, that is a key moment. So perhaps your clients want to know precisely when can they expect their products. If running discrete event simulations allow you to see precisely what your lead time actually is, right? Because there's variability in the process. And another key point, a discrete event simulator is like a sandbox. You're using this to make decisions. You're using this to test hypotheses, right? So think of this as a sandbox, a low-cost alternative to figuring out what if scenarios. Ultimately, we're operations managers. We want to be able to make decisions. So the discrete event simulator is an excellent way of introducing changes to your process without actually implementing them before. So you get to test. It's an excellent tool for testing scenarios and for testing different alternatives and see which one works best. So with that being said, thank you very much for your time. I hope this was helpful. If you have any questions, please email me. This is Professor Felipe Rodriguez from the School of Management, Economics, and Mathematics at King's University College, Western University. Hope to see you soon. There will be more videos. The next one, I believe, may be about setup and batching processes, which is actually really nice. And if you need more information, go to the playlist for the operations management course, MOS 3330. So thank you very much, and I hope to see you soon. Bye.